good evening, everybody. As you know, we've got Ben McKeon speaking tonight, an avid space geek and first-year PhD student researching adaptive optics at the NUI Galway. He was fortunate enough to be introduced to the world of SETI last summer when he took part in an internship with Breakthrough Listen and the Berkeley SETI Research Centre. An active member of the NUIG Astronomy Society, he always enjoys talking about the wonders of the night sky. When he's not tinkering with his own telescope or designing a new one, I'm usually found running, reading, or knee-deep in a pile of Lego. It's nice to be a child. We all wish we were your age. That's what it is, Ben. No doubt about it. So can everybody please put their hands together and give a Mexborough and Swinton welcome to Ben McKeon. Thank you.
Thanks very much, everyone. I will just share my screen and we'll get started. Perfect. You can all see that okay?
Yes.
Okay, fantastic.
Perfect.
So yeah, thanks for the introduction there, Steve. As you've already said, I'm Ben McKeon. I'm a PhD student with the Applied Optics Group at the National University of Ireland, Galway. And my talk this evening is going to be on SETI and adaptive optics. So just to kick off the talk, I always like to begin with this quote because I suppose, again, it basically just sums things up as matter-of-factly as possible. I mean, there are only two possibilities, that we are either alone in this universe or we are not, and both are equally terrifying. So with that in mind, you might ask, well, why are we looking for aliens? Again, you might say in one sense, it's this search for ground truth to find whether or not we have company, or are we just looking to frighten ourselves? So with that in mind, I'm going to go and share the outline. So first off, we're going to start with SETI, and I'm going to give you all a little bit of an introduction into what that is and what's going on in the world of SETI of late. And then I will share a little bit about adaptive optics and my current research. So we'll get started with SETI first and foremost. So first off, what is it? SETI is an acronym for the Search for Extraterrestrial Intelligence, and it is the search for technologically advanced alien life in the cosmos. And we do this by looking for technosignatures, which are signs of alien technology, such as communication and light pollution. Again, this word is borrowed from the astrobiology community, use the term biosignatures to search for what wouldn't necessarily be intelligent life, but maybe microbial life, bacteria, anything like that wouldn't be as advanced. But obviously, I suppose the main goal of SETI is to look for intelligent alien life that would have capabilities at least equal to ours. So that takes place mostly in California, run by the Berkeley SETI Research Center and the SETI Institute, which are both based over there. And I was fortunate enough to do an internship with them last summer. So it was myself and a few other interns. Again, most of our projects would have involved looking for technosignatures such as radio signals, but I know a few of my colleagues were interested in what we have here, Dyson spheres, and looking at what kind of profile would be produced on a light curve diagram if a Dyson sphere was to be eclipsing a star rather than just simply an exoplanet or something similar. So SETI isn't exactly a new field, shall we say. Even the more I suppose the more familiar among us might remember, I suppose, all of the different sci-fi from way back when, like War of the Worlds and all of that kind of stuff. So again, it has been in science fiction for a while, but it has also been science fact as well, in the sense that back in 1959, Cooney and Morrison suggested using radio as a means of communicating across interstellar distances. And then this in turn inspired Frank Drake, who we can see on the left there, to set up Project Ozma. So what he did was he decided to observe two nearby sun-like stars at 1420 megahertz frequency, which is the hydrogen line frequency for anyone that would be familiar with that. This attracted Soviet attention, obviously, because it was the height of the Cold War. And I suppose if there was any hint of someone discovering aliens, it was always going to be a race to see who'd get there first. And even more recently, I know in the past few days, China have, with their new radio telescope, which is, I suppose, a replacement for the Arecibo dish that got damaged there 2 years ago. They claim to have detected alien communications, but then again, all of the articles related to that have since been pulled. So I think it might be a false alarm, unfortunately. But going back to the 1970s and 1990s, that's when the American government decided to get involved. So there was Project Cyclops run by NASA, and there were also citizen science projects run by the Planetary Society. And obviously the University of California had a stake in this as well. But then unfortunately in the early 90s, NASA funding was withdrawn due to, I suppose, a lack of results. I suppose we haven't found aliens yet, unfortunately. So I suppose the US government were getting impatient, and they decided there might be better ways to spend that money. So unfortunately, ever since, it has mostly been funded by private investors. And that's exactly what Breakthrough Listen is. So this was announced in 2015 at a big launch in London by Yuri Milner, a millionaire. He had Stephen Hawking along. So there were a number of different initiatives launched as a result of the Breakthrough initiatives, such as obviously Breakthrough Listen. But some of you might also be familiar with Breakthrough Starshot, which is another interesting plan to try and send a small spacecraft to our next nearest star system to try and take images of it. So in terms of Breakthrough Listen, $100 million was allocated to survey the centers of 100 nearby galaxies and 1 million nearby stars over approximately 10 years. Unfortunately, obviously things have been a bit slow with the COVID pandemic, so progress isn't quite there. I suppose things were obviously put on hold, unfortunately, but Breakthrough Listen at the outset was guaranteed 20% of the time on the Green Bank telescope, which we see here on the left, and then 25% of the time on Parkes. I've had the privilege to observe using Parkes, but unfortunately our observing time has been significantly cut. So we haven't managed to secure quite as much time as we would have hoped. But on the flip side, there are other radio telescopes that are being used for SETI searches recently, including LOFAR, which I also did a little bit of work with. And there's also Meerkat in Africa. So they're also coming on stream. So fingers crossed they might be able to assist with the search. So at least here in Ireland anyway, where I am, so what we've managed to do is using the iLOFAR telescope. I know there's a LOFAR station in the UK as well, if I am not mistaken. But what we did anyway was we used the data taken from NASA's TESS satellite, which is the Transiting Exoplanet Survey satellite, and we managed to create a list of stars that would be visible at certain times when we would be able to use the telescope. And then we would observe these stars using a telescope station in Ireland, and then another one in Sweden in Onsala. And then obviously what we would do then is we would compare the data from the two stations and see if there were any interesting signals that were detected in both. And this was what's known as dual site coincidence rejection. So basically what this means is that any flukes or any interference that would be unique to one site was automatically discarded. So again, it provides another way of proving whether a signal would be interesting or not. So to date, we've observed 38 stars, and unfortunately we have not managed to detect any extraterrestrial transmissions. But I have heard from a friend of mine who was involved in the project last year that they're trying to get more stations involved. I think there is a station in France that's going to be involved as well. So fingers crossed we might hear something in the not too distant future. So obviously, what is this all about? So again, we have a kind of a a simple enough equation here for, I suppose, giving a guess at how many alien civilizations we might expect to come into contact with. So obviously, N represents the number of civilizations, or star is the average rate of star formation, and then FP is the fraction of these stars. So what fraction of these stars have planets around them? And then within that, everything is kind of nested. So you're depending on, each condition is almost dependent on the last in a way. So if these stars have planets, how many of these planets could support life? How many of them actually develop life? And then how many of them then go on to develop intelligent life? And furthermore than that, how many of these intelligent civilizations develop the technology in order to send signals into space? And then finally, the last parameter, L, means the length of time they've been doing this. So I suppose radio was, I think, first used just under. So it'd be just a little less than 200 years. Radio started to come on stream. So again, I suppose in the grand scale of the universe, we haven't been sending out radio signals for a very long time. And given the finite speed of light, I suppose there's only a relatively small bubble around the Earth within which, if anyone was able to detect our signals, they might know that there was an intelligent civilization here. So moving on from the Drake equation, so we want to ask, well, do the numbers add up? So finding a reasonable value for each term is obviously quite difficult because we are our own yardstick here. We're obviously going to have our own biases and wonder, well, if this is how we would do things, do aliens do it the exact same way? And I suppose we've no answer to that. You know, we've no way of telling, well, is that a universal way of doing things, or is that just kind of, I suppose, a human idiosyncrasy? So obviously many people have tried to hazard a guess. Carl Sagan in Cosmos made a very optimistic guess of about 1 million. And then, but I suppose at the same time, a conservative estimate will give a worst case of about 100. So there are potentially, at a worst case scenario, 100 other intelligent civilizations we could communicate with. But we would probably need a little bit of luck in order to get there. Unfortunately, the Drake equation is not universal per se, in the sense that it deals with planets only. So we probably have to modify it if we wanted to deal with moons that might have life. For instance, like I know on Europa, under the subsurface ocean there's a talk that there might be life. Again, it may not necessarily be intelligent, but again, it might require modifying the Drake equation in order to factor in I suppose to factor in considerations such as those. And even with Frank Drake here, this is his number plate. So he is so optimistic that he believes that the whole equation will simplify to n equals L. So based on best estimates, the rate of star formation is about 1. And then he assumes that all of these stars have planets. All of these planets are capable of developing life. They do develop life. They develop intelligent life, and they develop life that can transmit signals out into the universe. So all of this just collapses to just, this is all equivalent to 1. So he believes that the number of civilizations out there is effectively equal to the length of time that they have been sending signals out, which implies that it is an absolute certainty, in his opinion, that there are intelligent alien civilizations out there. And the best attempt we have made at any sort of detection was made by Ohio University's Big Ear Telescope on August 15, 1977, which became known as the WOW signal. So the signal lasted for 72 seconds, which was the maximum amount of time the telescope could observe the signal for, because it was fixed, it couldn't move. And it was interesting because this transmission was at 1420 megahertz, which was the same frequency that Frank Drake used. But what is interesting now is that transmitting at 420 or 1420 megahertz is banned because that frequency is restricted for radio astronomy. So if anyone on Earth was to transmit at that frequency, they would be arrested. So that makes us believe that this is probably not a terrestrial communication, but unfortunately the signal has not been detected again, but it is still our best candidate as a call from ET. And just to explain a little bit about what happens here. So all of these numbers represent how many times above the noise baseline the signal is. So you have, I think it's 1 to 9 would be anywhere between 1 and 9 times above the baseline. And then they go into alphabetical characters then for, I think it's like A is 10 to 12, B is 12 to 14, and so on. So they got as far as Q and U, which is 36 or 37 times above the baseline, I think. So the chance of this being a fluke were obviously quite small. But again, like I said, it hasn't been detected since. So unfortunately, we don't have anything else to really compare it with. But more recently, using the Parkes telescope that I mentioned earlier, there was another interesting signal detected coming from Proxima Centauri, which is a much nearer star system. And it was identified using software called SETI, which was developed by the Berkeley SETI Research Center. This is used to separate ET signals from background noise. So this signal became known as BLC1, and it blew up in the media. I suppose there was lots of Vice articles, and a lot of the popular news outlets started to cover it as a potential discovery of an intelligent alien civilization. But unfortunately, to cut through all of that media bluster and to get into the nitty-gritty of the science of it, trying to find it again using a follow-up observation campaign didn't yield anything, unfortunately. And once the signal was reviewed once again, it looked like the most probable cause was just human radio interference. And unfortunately, this is quite a common problem in radio astronomy. So if we look here at the frequency allocations for the US, I don't think there is one for Europe, obviously. I think most countries tend to set their own. I don't think there's one EU-wide either. So again, I suppose this was the best I could go with. So if we look at the bright yellow bands here, those frequencies are reserved for radio astronomy. But then we see all of the different other industries and uses that are competing for radio frequency allocations. And I suppose if you were to try and listen out for different frequencies, it would be like the whole earth is screaming at you. So again, you're definitely looking for a needle in a haystack there. So like I said, radio astronomy has an awful lot to contend with, unfortunately. So yeah, like I said, it is a very difficult task as a result of radio frequency interference. And there are so many electronic devices that could throw us off the scent, from phones, local radio, and even air traffic. I can remember even last year, as part of the internship, we were given little radio receivers to use, and again, you could tune into local radio, the local air traffic very, very easily. So yeah, it made doing any other kind of radio work very, very difficult. Sure, we could use a bandpass filter, but unfortunately, this would only allow certain frequencies, and the issue there is we don't know what frequencies aliens will be transmitting on. So that is almost as good as a guess. You know, we don't have anything that we could use to pick one frequency over the other. And obviously, a growing issue here is Starlink, satellite constellations more generally, including OneWeb as well. Massive constellations. I've even seen them myself whenever I've been out with my own optical telescope. But obviously, these satellites will transmit at a certain frequency. So if particularly you want to do high frequency radio astronomy, you're going to be contending with a lot of noise from satellites. So it's just going to be another headache for radio astronomy to have to deal with. So with that in mind, optical SETI is becoming much more common. So here we have the Lick Observatory's Automated Planet Finder, which is an optical SETI telescope. It's becoming increasingly popular because it isn't hampered by radio interference, but optical telescopes are obviously a lot more expensive to build because you have to manufacture mirrors and lenses, and Testing all of those is certainly not cheap, neither is fabricating them. I'm learning that the hard way, unfortunately. But the thing is that these telescopes, rather than looking for communication using radio, for instance, these would look for exoplanets emitting light pollution and laser pulses or other markers of alien civilization, such as a new initiative that has been launched called laser SETI. So this is what it is. So what this is looking for is very short, very high power laser pulses that are almost used as a kind of a lighthouse effect, that are sent out into the universe as a way of saying, hey, we're here. But unfortunately, the issue with that is you need to be within the line of sight of that laser in order to detect it. And I suppose we don't, nor do aliens, have any idea what's the best direction to transmit in. And unfortunately, optical telescopes are also affected by light pollution and by satellite constellations as well. Like I said, I constantly see them when I'm out with my own telescope. So that's not a problem that is confined to one type over the other. So moving on from a little bit about SETI, I'm going to talk a little bit about my own current research. So that is on adaptive optics. So what are they? Basically, they're just used to correct for the effects of atmospheric turbulence. And this is particularly pronounced for large mirrors on some of the largest telescopes in the world. So usually what happens is if your primary mirror is usually larger than about 4 meters, you'll need adaptive optics to be able to get image quality that you would expect given the large size of the mirror. And they're usually standard on most of the world's largest telescopes, such as the Keck and Subaru telescopes, which are all based in Hawaii. I know that the Giant Magellan telescope and the 30-meter telescope, which are being built in the Canaries and in Hawaii as well, also have adaptive optic systems, as does the European extremely large telescope being built by ESO in Chile, which I am doing a little bit of work on. So pretty much any large optical telescope nowadays comes with adaptive optics as standard. So if we look at these images here, we see the 2 Keck telescopes and the Subaru telescope, and we see they're shooting lasers into the night sky. I'll explain a little bit more about those in a while, but what they're called is laser guide stars, and they're used as a way to sample the atmosphere. So why should we use adaptive optics? So obviously, as light reaches us from, I suppose, the depths of the galaxy and the cosmos at large, it's passing through a vacuum. So the light isn't refracted or bent much, but then once it reaches the Earth's atmosphere, it is then refracted, much like I suppose we see here with the image of the dark side of the moon by Pink Floyd. We see that the light ray comes to the prism, and then obviously it's bent and dispersed out into all of its different colors. Obviously, the effect isn't that pronounced with the atmosphere, but the issue is, unlike that prism, the amount by which that light is bent will vary depending on factors such as temperature, humidity, altitude, and even, I suppose, the choice of location. Some areas in the Earth tend to be, I suppose, more suited to optical astronomy than others. Like I said, the effect is usually small, but then again, if you're going to the effort of building a mirror or a telescope with a mirror that is, I suppose, for the ELT, which will be the world's largest, it's nearly 39, I think it's 39.8 meters is the size of the primary mirror. So if you're going to the bother of building a telescope with a mirror that large, you might as well go the whole hog and use the necessary adaptive optics to get the image quality that you would want from such a massive investment. So why we need these? So again, this diagram here that I made here, I think this explains things quite nicely. If you think of the atmosphere as a type of patchwork quilt, so you will have areas in the atmosphere where there will be a lot of turbulence, and then there'll be some areas that aren't as turbulent. So obviously, if we think of the atmosphere being made up of patches of turbulent and non-turbulent air, so obviously as the light waves are traveling through space, they're all fine because it's a vacuum and it's not bending the light at all. But then once that reaches Earth's atmosphere and the light rays are passing through 2 patches at the same time, we have a patch of negligible turbulence and then a pocket of turbulent air. And then we see here that the light is bent much more as it goes through the turbulent pocket rather than the non-turbulent pocket. And we use this symbol here we call R0 or Freed's parameter, which usually determines the average length of turbulence within the atmosphere. And then here we have images of Saturn and Uranus when viewed using adaptive optics when it's turned on and when it's turned off in the near infrared. So obviously we see that the images are much clearer once we do use an adaptive optics system. So how is an adaptive optics system constructed? So obviously it's made up of different components, such as the deformable mirror, which is needed to change the shape to match the incoming light waves. So obviously, if we look back on this slide here, we see that the light wave is bent by different amounts. So what we have is a deformable mirror that is able to match the shape of the incoming light waves in order to correct for any errors that might be introduced by the atmosphere. Like I said earlier about the lasers being shot into the night sky, so we need guide stars. And these are light sources that are used to sample the turbulence present in the atmosphere. And obviously, in the case of the images we saw earlier, they're not necessarily actual stars, and laser guide stars are becoming more and more common because it allows you to use adaptive optics anywhere on the sky rather than having to use it in the vicinity of a sufficiently bright star that you could sample enough of the atmosphere. And then obviously, once you have this information, you need to pass it to a wavefront sensor, which measures the difference between the refracted light waves and, I suppose, a hypothetical ideal. There are several types of sensors available. I'll probably explain a little bit more about one that I have looked at in detail in a minute. And obviously, the deformable mirror doesn't magically just change shape on its own. We need actuators to change that shape. And then we need a control algorithm which handles the data from the wavefront sensor and then commands the actuators to change the deformable mirror to the required shape. And usually we need to do this up to almost 1,000 times a second, depending on the types of aberrations we're trying to correct for. So then, so my research to date has focused primarily on wavefront sensors and control algorithms. So this is a wavefront sensor in particular that I have looked at in some bit of detail. It's called the pyramid wavefront sensor and is the most sensitive wavefront sensor available. So the primary element is a glass pyramid, and trying to manufacture that is very, very difficult, particularly trying to machine the tip of the pyramid here. You want to get that as close to a point as possible. But from what I've seen in doing some element of optical testing, there'll always be some finite width there. So trying to manufacture a perfect pyramid is nigh on impossible. So these pyramid wavefront sensors tend to be deployed in extreme adaptive optics systems, which are capable of very high quality imaging. However, the only problem with these, as much and all as they are quite sensitive, their main issue is that they only produce useful information once incoming light is focused to within a very small region of the apex of the pyramid. So usually what we do is we can move the tip of the pyramid around and the light will be diffracted into each of these images, more so one than the other once the pyramid is moving. So that way we can increase the range over which the pyramid sensor is useful. But unfortunately, this does decrease its sensitivity. So one of the main problems within wavefront sensing at the moment is trying to find a nice trade-off between the sensitivity and the range over which we can use the sensor. There are other sensors available as well, but this is becoming the most popular far and away because of the sensitivity that it provides. So when we talk about control algorithms, obviously we need some way to be able to reconstruct the incoming light waves from sensor measurements. So we need some kind of mathematical formula to describe the atmospheric turbulence. The Zernike polynomials are usually used. This is what these are here, and they correspond to different aberrations. So if we look at this here, this one corresponds to just a shift of the wavefront. These ones here correspond to the wavefront being tilted in X or Y directions. And there's other ones such as defocus, spherical aberration, astigmatism. From what I've heard, I know a few friends of mine who have had their eyes tested have been told they have astigmatism. So again, telescopes also suffer from the same issue. So the Zernike polynomials, because they describe these effects, they seem like a natural choice, but they're not the only one we can use. And this is particularly an issue depending on the shape of the telescope's opening. Usually we assume it is circular, but particularly with these Zernike polynomials, they assume that there is no obscuration of the telescope aperture, which is rarely the case, even with amateur telescopes, like I suppose even my own Newtonian, its secondary mirror gets in the way, and even it'll be the same for a Schmidt-Cassegrain or just about anything really. So because of that, these do not possess the correct properties, and we need to use a different set of polynomials. For instance, if it is annular or even square or hexagonal in rare cases, again, different polynomials would need to be used in those instances as well. So then once all of this data is collected, the deformable mirror uses this data, and the control algorithm is then capable of filtering out the adverse effects of the atmosphere. So we get the images we saw, like Saturn and Uranus a few slides ago. And we have another example here. So probably one of the main uses for adaptive optics is trying to directly image exoplanets rather than using light curve diagrams, which is the most common technique to date, where if a planet was to transit in front of a star, obviously there'd be a dip in its light curve. And based on that, we're able to infer the presence of an exoplanet. But rather than that, what we would prefer to do is we would prefer to be able to image these directly, and even on top of that, be able to, I suppose, make discoveries based on their atmospheres and see, is there any way of telling whether there might be life on such planets, even at such great distances. So here we have two images here. We have a star, and then we have a planet 2M1207b. And then we have two different planets that are orbiting a host star here. And again, all of these pictures have been gathered by ESO. So fingers crossed, once the ELT comes online in 2026 or 2027, we'll be able to discover more exoplanets in a similar manner. So the future advances of AO and SETI. So like I said, adaptive optics is going to be integrated into the ELT in Chile. The instrument that's going to do that is called MAURI, which stands for Multi-Conjugate Adaptive Optics Relay. That's what I'm working on at the moment. This is an image, a render of what it'll look like once it's finished. Another interesting advance is using artificial intelligence control algorithms, which in some instances prove more adaptable when dealing with atmospheric turbulence. Usually when conditions change quickly, in some instances, artificial intelligence has proven to be more flexible in dealing with these changes. And even to push that further, they're looking at using adaptive optics without wavefront sensors. So rather than using a sensor to control a deformable mirror, they're trying to just take the raw data in and carry out all corrections in post-processing. Another interesting use of optics, not necessarily in the mirrors and lenses sense, but the solar gravitational lens is a plan to use our own sun as a lens, and the gravitational lensing effect produced by that to be able to image very distant exoplanets. But obviously adaptive optics is going to be required for the success of this project. And the overall aim of all of that would be to increase the resolution to image exoplanets in greater detail. So we're not even just looking at, I suppose, a fuzzy blob. We're able to sharply image the exoplanets using the solar gravitational lens, and even be able to map their continents, their oceans, their atmosphere, even their settlements in greater detail. So in the meantime, before all of that comes online, obviously, having seen optical SETI, you're probably thinking, well, what's the point of radio SETI? It is certainly not redundant, and it's still a very valuable asset to the SETI cause. There's still plenty of data being produced by it that needs to be trawled through. So it's not going anywhere anytime soon. So unfortunately, though, SETI proposals do rarely get any time on the world's largest optical telescopes. Usually, if you wanted to, I don't know, if you wanted to use the James Webb or the ELT or even Hubble, it would be very difficult to put in a proposal to look for extraterrestrial intelligence, because unfortunately, I suppose the field tends to get a bit of a bad rap. It's kind of lumped in with kind of, you know, kooky kind of UFO kind of conspiracy theory types, which isn't necessarily fair, but fortunately, that's how things tend to be. So a way to remedy that would probably be join an interest group. Again, I'm preaching to the choir here. You're all members of an astronomical society, so you're already members of such a group. But I suppose myself, I'm a member of the Planetary Society also, and one of their main areas that they like to focus on is to discover life. So again, SETI is definitely high on their list of priorities. And even if we do completely scour the universe and find that there are no aliens, that might not necessarily be a problem, because I'm sure there's plenty of new physics to be discovered along the way. And even if we think back to Jocelyn Bell, who discovered the first pulsar back when she was a student in Cambridge, what they thought was an alien civilization happened to be a pulsar. So I'm sure there are plenty of other discoveries to be made in a similar manner. So that has been my talk. Thanks very much for having me. And if anyone has any questions, I would love to answer them now.
Ben, thank you for an interesting talk. And could I ask you to stop sharing your screen, please?
Certainly.
So you can see the rest of the usual suspects.
Sure.
I'm just going to go back to, and the usual routine, please, ladies and gentlemen. A digital hand, if possible, wave at me otherwise. We'll start off with Mick Nichols, please. Mick?
Do you think that the Drake equation now needs a complete overhaul, because it's based on what they thought they knew then, not what we know now? And also, I believe a few years ago, someone did some research on the WOW signal, which suggested it might have come from a comet.
Yeah, I'd heard that hypothesis as well, that it had come from a comet. I know that Breakthrough Listen have tried to, I think a few years ago when Oumuamua was passing through the solar system, they had pointed their telescopes to try and observe it, to see if any similar signals were coming from that, to see if there was any sort of similarities between that and the hypothesis that the WOW signal may have come from a comet. But unfortunately, at least in the case of Oumuamua, it didn't seem like there was anything transmitted. So again, that hypothesis still needs a lot of further work.
Okay, Nick.
And on the first part of my question, do you think that the Drake equation needs an overhaul?
Oh, absolutely. Yeah, no, it definitely does. I've seen a few papers written that people have started to modify it, that they've tried to find that it's not simply just a product of a bunch of different terms, and I suppose there's a lot more nuance there. So it absolutely does need to be modified. It's not as simple as that. Yeah, absolutely.
Thank you.
Okay, thank you, Mick. John Leach.
Hi there, Ben. A fascinating talk. All the while I kept thinking about. Let me close this window. We got dogs bark.
Whose dog is it?
About 3 miles away. We're talking about artificial intelligence, which comes in everywhere. And then, of course, you came out with a slide, and you basically said that it's used in control algorithms. Now, I use a lot of software which has got AI, but it's for objects such as humans or things that we know of shapes and sizes.
Okay.
How does AI come into effect in the atmospheric turbulence when you don't have the reference images to model on?
Well, you see, that's a big issue that people are trying to solve at the moment. And I think the problem with AI more generally is explainable versus non-explainable AI, from what I've heard. The big issue is it's kind of being treated like a bit of a black box. And I think the problem is that people tend to see if it produces a positive result, they think, oh, great, we're just going to run with this, you know, rather than actually taking the time to understand. And from what I've seen in a few different papers that I've read, the amount of training data needed to be able to differentiate between, I suppose, a turbulent state and a non-turbulent state, even if you don't have a perfect, ideal kind of yardstick, shall we say, is enormous. Like, I know there's some algorithms that would take 36 to 48 hours to train. So again, it could be a while yet. We might need an improvement in computer hardware rather than, I suppose, telescope quality in terms of getting AI to the level where it needs to be in order to be able to work on telescopes in that capacity.
Yeah. I mean, it's got mileage, and you know, AI has been used now for nearly 40 years. You know, it's software. I was certainly back in the 80s. But it's the way forward, isn't it?
Oh, absolutely. I completely agree. Even in other fields, from what I've seen, it's just about everywhere. So yeah.
Thanks very much indeed, Ben.
Yeah, thanks a million.
I haven't got a question from Mick. Please go on.
You mentioned a couple of different techno-signatures.
Mm-hmm.
How have they changed in the last 60 years, and do you see them changing again in the near future?
As in, you mean the different, like, as in how do the different techno signatures...
Well, you've been looking for radio signals. What are you looking for now?
Okay.
And do you see those changing as our technology evolves?
Mm-hmm. So again, I suppose this question comes down to the problem of us being our own yardstick, in the sense that, I suppose, back in the day, it would have been, oh, well, we use a lot of radio technology. We're going to be sending signals out into the cosmos as a result of using that technology. Well, maybe there's alien civilizations that do the same, in the same way that, again, if you were to look at Earth at night, you would see all the different cities lit up. So would there be a way, once, I suppose, adaptive optics has gotten to a level where we would be able to look for evidence of alien light pollution for different settlements or anything like that? And even as technology advances on our own end, if we were to assume that there are alien civilizations that advance at a roughly similar pace, what we might be able to do is to, again, use us as our own yardstick. So if there's any sort of future technology that we use, would we be able to find any sort of evidence for alien technology that is in some way similar, and the different kind of fingerprint of that, should we say? So to answer your question, yes, I do think the technosignatures will evolve, but it's almost at a point where there are sort of unknown unknowns. Like, there might be technosignatures out there that we might have no idea, you know, we might not even know that they're technosignatures because maybe our technology isn't even advanced enough to detect them.
Okay, Loz?
So mine's maybe a little bit more around an opinion piece, more than sort of the scientific side of it. So through the last sort of 20 or so years, obviously SETI has become more and more sort of prominent.
Yep.
But there's been a lot of sort of research groups come and gone, and a lot of sort of, certainly the back end computational side sort of come and go, and it's all been due to diminishing returns within the research sector. Is that a common problem? I mean, how do you see funding in the future? I mean, a big one is, say, SETI at Home closed down in 2020, I think it was, and I know there's a couple other groups which have closed down, and it's all due to the diminishing return based on the funding that they were receiving and the amount of effort that was going into it.
Yeah.
So where's the funding coming from, sort of long term, I think is probably the question.
My best guess, again, I suppose, again, like the biggest thing was, again, during the Cold War, it was all governments had a stake in this because they wanted to be the first to discover some kind of alien civilization. But then, I suppose, as we began to look, there didn't seem to be much there. And obviously, they kind of came to the conclusion, look, we're wasting our money here. So again, with the Berkeley SETI Research Center, funding is mostly private. It's mostly privately funded. Like Breakthrough Listen, for instance, was funded by Yuri Milner, who's a millionaire or billionaire even. So again, he was just a donor who gave all of this money. He believed the search for aliens warranted this investment, so he made the donation. But again, like I know from my bit of work with the SETI Institute as well, which would be another group that would be heavily involved in this. Again, they rely heavily on donations. I think they're a registered charity. So again, much like the Planetary Society, their membership would usually, I suppose, donate to them. So again, we're probably going forward, I see, going to have to rely mostly on private funding and trying to drum up enough excitement among, I suppose, ordinary kind of amateur astronomers and try to, I suppose, get them thinking, oh, well, if you give us a few quid, you know, you might be able to help with the search for extraterrestrial life. So I think it is mostly private investment, and a lot of good PR is what is going to be required in the future.
Oh, can we get someone more important to stop sticking Starlink satellites up and put their money into this instead?
Yeah.
Well, maybe we will manage to get him onto a space flight somewhere.
I'll send him an email later.
Right, okay. Peter Lloyd.
Yes, thank you, Paul. Thank you, Ben. That was a fascinating talk. I've always been slightly puzzled by the use of the hydrogen line for SETI, listening to SETI. And now you made it clear that one great advantage is that's a relatively quiet wave band in the sky. But presumably other civilizations will do the same thing. So we'll only pick it up if they're positively sending a message out at that frequency because they want to be discovered. And I'm wondering whether we are doing that at all.
I don't think that we, to the best of my knowledge, I don't think we're transmitting at the hydrogen line.
That's what I thought.
Yeah. I do know as well with laser SETI, there are, I suppose, within kind of optical, within the optical realm, I don't know how many attempts we make as humans really to send signals out into the cosmos because of the power needed to be able to transmit signals over those distances. Most of our SETI, I suppose most of our SETI resources goes into developing technology to be able to detect rather than to send out signals into the cosmos. I know there was obviously the Arecibo message back in the day, but besides, I think China have a similar, a new similar radio telescope like Arecibo. I think they might be able to use their telescope to do something similar, but I don't know if we would really focus on sending signals out as rather than taking them back in.
That's what I was on. The Arecibo message, was that sent at the hydrogen line frequency?
I don't think it was. No, I'm not entirely sure off the top of my head what frequency that was sent at.
It seems to me the greatest likelihood of our being detected is the general chatter that all our radio broadcasts and our television broadcasts and all this junk being sent out into space.
Yeah, absolutely. Like, I mean, for all we know, the aliens could be listening to the BBC.
Yeah. Well, thank you.
It's a horrible thought, really, isn't it, that our first interstellar contact could be somebody watching Ina Sharples from the mid-1960s. But there you go. Whilst we're talking about Ina Sharples from the mid-1960s, Ben, your discussion didn't mention at all cosmological time. And, you know, a human being's only around for 80, 90, 100 years. And we've only been transmitting radio signals. If you include any chatter that might have leaked away used by the Morse telegraph, then, yeah, you said 200 years. Isn't there a real isn't there a real possibility that we are the only intelligent life form that has technology at this time in our universe? And unfortunately, before anybody or any other civilization gets up there, we'll have either succumbed by our own hand or by some other natural phenomena.
Yeah, I suppose you're right. I didn't mention it in the talk exactly, but I know that that is a very existential question that tends to surround this debate. I mean, if we are the first, maybe other civilizations haven't had the chance to evolve yet and develop the technology that we currently have. Or I know the term that's usually used surrounding this debate is the great filter, that there is some sort of almost sociological effect that advanced civilizations may tend to just destroy themselves, so that if any civilization that came before us maybe had the opportunity to develop this technology, that they might have ultimately, unfortunately, blown themselves up. So I suppose it definitely begs the question that we hope we won't suffer a similar fate. But again, yeah, there is definitely a certain element of luck involved in us, and if there's another alien civilization out there that are capable of this communication, that if we want to sustain it, that we'd need a bit of luck that we're both kind of on the same time scale, like you said. Or if there's any alien civilizations out there, are we detecting transmissions from eons into the past? And if so, is there any way of us to be able to decode them, to make sense of them? So yeah, there's tons of questions that come with this issue of timescale.
Okay, cool. I'm looking around for any Roy.
Yeah, it's just a comment more than anything else. There was a Sky at Night program earlier this week with Martin Rees, and he was talking about a similar thing about civilizations and the possibility that civilizations get technologically advanced enough that actually the machines take over. You know, the computer systems, they become the civilization. And the other thing that was talked about was the fact that actually we're losing the radio, because we listen to radio now on things like Alexa or down through cable, through Wi-Fi. Your TV is done, Netflix and Disney Plus is done down via cable these days. So we don't have that use of radio in a civilization is lowering down to a certain extent.
So we're becoming a less radio noisy world.
Yeah.
There's the point. We're making the assumption that any civilization would use radio.
Yeah, exactly.
We communicate by sound. They may not communicate by sound. And what they use as communication may be beyond us. I mean, both voices talk to one another, but we don't understand them.
Yeah, that's very true. But as well, I suppose, like you were saying there, the fact that radio is, I suppose, being phased out more and more as a result of, like you said, Alexa and all of this, all of these other opportunities to listen to the radio over the internet or any other means. But I know as well a big application of adaptive optics is optical free space communications. So rather than communicating using radio waves, you'd be able to communicate using laser or something like that. And again, is it going to evolve that the search for SETI is going to go that way? And again, are we going to fall for the same kind of bias there that, oh, well, I suppose we started with radio and then we evolved to laser and then hope that we can decode their transmissions. But like you said, we might have no hope of being able to understand what's being said. So again, it's the big weakness of this kind of search is that it's ultimately a literal shot in the dark.
So
sort of space debris and sort of chaff from stopping the radio signals from coming to us and being blocked, and they are being sent. We're just not receiving it because space, even though it's big, you know, there's a lot of stuff out there.
That is definitely a very, very valid question. And I do remember last year, I saw a paper on it briefly when I was working with the SETI Research Centre, that there was a plan. Again, it's all hypothetical. There's been no money allocated to this. It was just a kind of a concept that was just put forward, putting a radio telescope on the dark side of the moon. So that way you avoid all of the space debris, all of the interference, and all of the other all of the kind of the radio chatter coming from Earth, even though that might be on the way back. But you get a much quieter you get a much quieter place to do radio astronomy from on the dark side of the moon, and obviously you don't have any of that space debris to be able to contend with. So it would be an interesting concept, but getting the money allocated for a project like this, one, and two, building it would also be another very very serious undertaking.
We're going to take two more questions. Mick Nichols.
Yeah, it was interesting just listening to that other debate a few minutes ago about, for example, having so far advanced technology that we couldn't detect it.
Yeah.
But the thing is, they've got to reach that advanced technology first. They can't just become humans and obviously, oh, we've got all this singing, dancing technology.
Mm-hmm.
We had bows and arrows before we had bullets.
Mm-hmm.
So, you know, we'd still detect that primitive, if you like, signals what they're sending out before they add the massive advanced technology what we can't detect, surely.
Yeah, I suppose that's very true, because I suppose the speed of light as well. Again, there's kind of a hypothetical idea that to a civilization 80 light years away, I mean, it'd be the Second World War, you know. So again, if they had, or if a hypothetical alien civilization had the necessary technological wherewithal to be able to assemble a telescope that had that level of detail, that they were able to resolve Earth to that scale, they would see Europe in tatters. So again, that's definitely a very valid point, in the sense that, again, if we were able to do the same going the other way, we would have we would only be able to see them as they were, depending on what our distance is. So obviously, the further away they are, we're going to be looking at them further back in time.
It was saying with all that palaver around Tabby Star, weren't it? It's a Dyson sphere, it's this, that, and other, and they're building a Dyson sphere, but they're doing it silently, and we aren't sending out a signal. That's amazing. That.
Exactly. Yeah. All of that stuff. I think that was BLC1. I think that was to do with Tabby Star. So yeah, again, the fact that it was silent was a bit odd.
Yeah, exactly. Build something like that, but don't send out a signal and do it silently. Don't think so.
It's an interesting thought, that, Mick, that we could end up watching somebody else's version of Eva Sharples in years to come.
Well, it can't be any worse than what we're watching now.
One last question then from Peter Lloyd.
Yeah, can I add a question on the adapted optics part of your talk? I think I heard you say that it was getting to the point where all the modifications that adaptive optics does can be done in post-processing. Now, did I understand that correctly, that you can now do it without a deformable mirror telescope?
As in, that's where they're hoping to go eventually. But again, technology is a good way off that. Talking to one of my supervisors in the college at the moment, he was saying that technique is very popular for biological imaging. So again, if you're trying to image cells in some kind of liquid, you would probably be able to do all of the necessary post-processing or do all of the necessary aberration correction in post-processing. But unfortunately, when you're dealing with the atmosphere that is subject to changes that happen multiple times a second, almost up to 1,000 times, again, we're going to need much more powerful computers to be able to correct for that and to be able to deal with the data throughput that's coming there as well. So wavefront sensorless adaptive optics, again, it's quite a new field. That would be the end goal, to be able to develop telescopes that have that capability, but it is still quite a way off yet, I'd say.
Yeah, and you would need an enormous frame rate.
Oh, absolutely, yeah.
It's just exciting because it's the sort of thing an amateur might be able to use, because we can't afford the deformable mirrors.
Definitely, yeah. I think it would be nice to be able to bring adaptive optics to even amateur astronomers, and almost one day hopefully get it to the point where pretty much every telescope has it. So
not in my time, I fear. Thank you.
No worries.
Okay, ladies and gentlemen, I think that just leaves us to give Ben a big Mexborough and Swinton Astronomical Society thank you. Ben, thank you very much for a very informative and enjoyable talk. Thank you very much.
My pleasure.